Welcome to the lecture on network analysis module 4. In this module, we will discuss LP and dual LP solutions to network problems. Network problems are usually solved by using part and CPM techniques. These problems can, however, be solved by using LP technique. In a network problem, there may be a number of activities resulting in a number of constraints. Therefore, sometimes it may be desirable to formulate the network problem by an LPP. Before we proceed to find the LP solution of a network problem, let us have a quick look at the differences in part and CPM. CPM network is activity oriented. It is constructed on the basis of activities, whereas part network is event oriented. It is constructed on the basis of events. In CPM, activity time is deterministic, hence only one time is considered, whereas part network deals with uncertainties and 3 time estimates are considered usually: optimistic time, most likely time and pessimistic time. CPM times are deterministic and known and are related to cost. Therefore, crashing of activity duration is possible, whereas in part, as there is no certainty of activity time, crashing of activity duration is not possible. So, these are the main differences in part and CPM techniques. Now, we proceed to find an LP solution to network problem. In the network problem given in the following figure, clearly the double line arrows show the critical path 1, 2, 3, 4, while the activities 1, 3 and 2, 4 are non-critical. They are non-critical activities and they have some slacks. To formulate this network problem as an LPP, we denote xi as the earliest occurrence time of event I. Then the network problem can be formulated in the following LPP. Our objective would be to minimize x4 minus x1. x4 is the earliest occurrence time of the final event and x1 is the earliest occurrence time of the first event. So, we want to minimize the time difference between the first and the last occurrence events. Then we have some constraints. From the diagram, we can easily write for the activity 1, 2, x2 minus x1, that should be greater than or equal to 7. Similarly, for the activity 1, 3, x3 minus x1 is greater than or equal to 9. for the activity 2 3, x 3 minus x 2 greater than equal to 3, and for the activity 2 4, x 4 minus x 2 greater than equal to 5, and finally for the activity 3 4, x 4 minus x 3 is greater than equal to 4. Here the right hand quantities of the constraints denote the activity times. Obviously, all the variables xi's are non-negative. So, if we want to solve this problem by using simplex, we have to convert this minimization problem into a maximization problem, and then we have to convert this constraint into equations by introducing surplus variables and, if needed, artificial variables. Here we introduce the surplus variables S12, S13, S23, S24 and S34 for the first, second, third, fourth and fifth constraint, and even we introduce the surplus variables, we are not getting the initial basic feasible solution to start with the simplex. Therefore, we need to introduce 5 artificial variables, and obviously the minimization problem should be converted into the maximization problem. So, after doing all these things, if we set the problem in simplex, the simplex looks like this as shown in the slide. In the basis, we have the vectors a1, a2, a3, a4 and a5, and the corresponding variables we take as x10, x11, x12, x13 and x14. And if we find the zj minus cj value, then we see that z4 minus c4 is the most negative, hence a4 will be the entering vector, and from the minimum ratio we can easily determine the departing vector, which is here a5, and then we can proceed as usual for the next iteration. Finally, we can get the iteration as shown in the slide. We see that in the basis we have the vectors a2, s24, s13, a3 and a4. zj minus cj is greater than or equal to 0 for all j. This indicates that the optimality condition is satisfied. Hence, we can read the solution from this final table. The final table shows the earliest occurrence times xi as the basic variables x2 equal to 7, x3 equal to 10, x4 equal to 14, s13 equal to 1 and s24 equal to 2, whereas the non-basic variables x1 equal to 0, s12 equal to 0, s23 equal to 0 and s34 equal to 0. This means that the critical path contains event 1, 2, 3, 4 with respective earliest occurrence times, and the latest occurrence times are 0, 7, 10 and 14. Please note that the slacks S12 in the path or in the activity 0 for the activity 2, 3, 0 and for the activity 3, 4 equal to 0. That means the activity 1, 2, 2, 3 add 3, 4, they make the critical path, while the slacks for the two non-critical path activities 1, 3 and 2, 4 are respectively 1 and 2. Thus, we see that the final linear programming table contains the same information as the conventional network model already shown previously, as well as it is showing in the slide. We were discussing the LP solution to network problem. We have seen that a small network problem results in a large linear programming problem. That is why LP approach is sometimes computationally undesirable. However, dual LP approach can reduce the computation slightly, which I am going to show you in the next few slides. Dual LP solution to network problem. If the linear programming problem already formulated in the previous section is called as primal, then we must have an analogous dual counterpart. The formulation of dual LP is quite different. The dual gives the network problem a network flow interpretation. The starting event is viewed as a source, while the terminal event can be considered as the sink. The decision variable Vij can be defined as the flow through the activity Ij, and the activity duration can be considered as the cost Tij of sending one unit of flow from I to j. By these definitions of this problem is to find the longest path, that is the critical path, which is equivalent to finding the highest cost route through the flow network. With flow Vij at cost Tij, the objective function which is to be maximized is given by f max is equal to sigma Tij Vij summation over I and j. Here Vij's are restricted to the flow in the network. With positive flows into an event and negative flows out of an event, the constraints imposed on Vij are called the balancing equations. The starting event has a flow out of -1 and the terminal event has a flow in of +1. Therefore, we can write minus sigma over j V1j equal to minus 1 and sigma Vin is equal to plus 1. For all other events, the flow in will equal to the flow out. Therefore, summation over I Vik minus summation over j Vkj should be equal to 0 for all k not equal to 1 and n. Each event contains a constraint representing a flow balance. Thus, the problem can be formulated as F max equal to summation Tij Vij subject to minus sigma V1j equal to minus 1 for all j, sigma Vik where summation varies over I minus summation over j Vkj equal to 0 for all k not equal to 1 and n, and summation Vin is equal to 1 for all I, and obviously Vij greater than equal to 0 for all I and j. We now formulate the network problem given in the figure as maximize f dash equal to 7 V12 plus 9 V13 plus 3 V23 plus 5 V24 plus 4 V34 subject to V12 plus V13 equal to 1, V13 minus V23 minus V24 equal to 0, V13 plus V23 minus V34 equal to 0, V24 plus V34 equal to 1, and Vij's are greater than equal to 0. In the previous section, the primal problem as derived was minimize f equal to minus x1 plus 0x2 plus 0x3 plus x4 and subject to the constraints as shown in this slide. Considering dual variables V12, V13, V23, V24 and V34, the dual of the above problem can be written as maximize f dash equal to 7 V12 plus 9 V13 plus 3 V23 plus 5 V24 plus 4 V34 subject to the constraints as shown in this slide. It is to be noted that the problem, the dual problem given in 5 is a special case of the dual 4 or primal 3. Therefore, we now solve the dual problem as shown in this slide. To solve this problem, we have to introduce some artificial variables for each constraint, equality constraint, in order to get an initial basic feasible solution to start with the simplex. Here we introduce V6, V7, V8 and V9 as the artificial variables, and then the problem is converted into the form as shown in this slide. Now, we proceed to solve this dual problem by simplex. In the first iteration, we see that the vectors A1, A2, A3, A4 are forming the basis, and from the values of Zj minus Cj, we see that A2 is the entering vector, and proceeding similarly as we already done in simplex, we can find the departing vector, and finally we could reach to the final iteration. Here in the basis we have the variables V34, V12, V23 and V7. Since Zj minus Cj values are all non-negative, we can claim that the optimality condition has been satisfied. And from the final table, we read the solution as V12 equal to 1, V23 equal to 1, V34 equal to 1, and the non-solution variables are V13 equal to 0, V24 equal to 0, and the value of the objective function f max is equal to 14. Thus, the unit flow will proceed through the branches V12, V23 and V34. This means that the longest route in the network is along the path 1, 2, 3, 4, which is clearly the critical path, and the total project duration is 14 weeks. The slack for non-critical path activities is obtained from Zj minus Cj rho in the final table. If one unit of V13 is entered into the solution, then Zj minus Cj indicates that the objective function will be increased by +1. And if V13 is entered into the solution, the new route will have a duration of 13 weeks instead of 14 weeks. The new route is 1 week shorter than the critical path. This implies that the activity 13 has a slack of 1 week. Similarly, from the Zj minus Cj value for V24, we see that a new route with V24 will be 2 weeks shorter than the critical path. Therefore, the activity 24 has a slack of 2 weeks. So, this shows that the dual provides the same network information as the primal. Before I conclude this module as well as this chapter, let me introduce some advanced topics in network analysis. Network updating. Updating means study of the progress that has been made and its impact on the remaining activities. The time estimates made before may be incorrect. A particular activity may take less or more time. So, by modifying estimates of time on various activities, the remaining network can be redrawn. This is known as network updating. Resource leveling. There are various activities in a project demanding varying levels of resources. When a project is to be managed with available sources, the demand on certain specified resources should not go beyond the prescribed level. This operation of resource allocation is called resource leveling. And finally, resource smoothing. When the main constraint is project duration time, the demand for resources are smoothened by shifting the activities having floats. Here, total project duration is maintained to the minimum level. In this module, we have discussed thoroughly the LP solution and dual LP solution to network problems. Though network problems are usually solved by part and CPM techniques, those problems can be solved by using LP technique. From our study, we have seen that LP technique is not always computationally efficient. With these remarks or comments, we end this module as well as this chapter.